us look at these questions. The structures of citric acid and isocitric acid are shown. So this is citric acid and this is isocitric acid. How many chiral centers does each acid possess? Okay, now let's look at citric acid first. We look at each carbon one by one. So the first carbon here, what kind of things are we going to look at? Chiral center. Chiral center means a carbon that linked to 4 different groups. Okay, 4 different groups. So you need to know carbon that linked to 4 different groups is chiral carbon. So it must have 4 different groups in order to become a chiral carbon. So now let's take a look on the carbons here. The first carbon, this carbon, it has 2 hydrogens. So obviously it does not fulfill the conditions where chiral carbon has to stick to 4 different groups or atoms. So it doesn't fulfill that. So I make a cross there. This is not a chiral carbon. So let's move on with this one. This one, COH, and up here, CH2CO2H, down here, CH2CO2H. So this is not a chiral carbon as well because it linked to CH2CO2H and CH2CO2H, which is the same group. So we disqualified this carbon. Now let's look at the next carbon. How about this carbon? This carbon, again, this is disqualified because it has 2 hydrogens. So we disqualified this. And how about these 3 carbons, which is the carbons at the CO2H, CO2H, and CO2H. So we know that CO2H has double bonds. So if it has double bond, we can just ignore it, or we can just disqualify it straight away, because as long as it has double bond, it fails to fulfill the situations where it has to link to 4 different groups. Okay, so you see the carbon here just has 3 groups in maximum. Because of the double bond, it has only 3 different groups. So we can just disqualify them. So we disqualified the carbon here, here, and here, and end up with there is no chiral carbon, 0. Okay, 0. So it's either C or D by now. Now let us look at isocitric acid. Isocitric acid. So this carbon is not a chiral carbon because it has 2 hydrogens. CO2H beside it, CO2H, disqualified. As what I said, it has double bond, and hence it links to 3 different groups instead of 4. Okay, so chiral carbon cross, I cross all the CO2H. Okay, I cross all the CO2H. Now let's look at this carbon. So this carbon is a chiral carbon, actually. It's a chiral carbon. So I put a star here. Okay, why? Now let's take a look. This carbon up here, it linked to CH2CO2H. This is one group. The second group is H. Okay, H. By right, if we draw it out, it's supposed to look like this. Okay, so H up here, CH2CO2H. On the right, CO2H. At the bottom, CHOH, CO2H. So this is a chiral carbon because it links to 4 different groups. So as you can see clearly, this Okay, let me put a circle. The first one, the second one, the third one, and the fourth one. They are different. So hence, that carbon is chiral carbon. What else? Let's look at this one. This carbon is also a chiral carbon. So let's look at Y. Okay, so look at Y. Now, okay, I put some arrow. This one is for this, and now let us draw the carbon here. Okay, so let us show clearly why this is 4 different groups. So let's say I put this carbon at the center. Now let's work out the 4 different groups that it takes. So first, I'm going to put as you can see this. Okay, I circle it in red, so you can see there is a hydrogen there. Okay, so and then there is a OH, there is a CO2H. Okay, so these are the 3 different groups. Okay, so I write down H, OH, CO2H, and on top of that we have this big group, so which is C CH CO2H and CH2CO2H. Okay, so this carbon is a chiral carbon because it links to 4 different groups. Let us see which are the 4 different groups. The first one, on top we have this big guy, and on the left you have hydrogens, at the bottom you have OH, on the right we have CO2H, 4 different groups, and hence isocitrate acid has 2 chiral carbon. So 2 chiral carbon, and hence the answer is